This is 1986 AP Physics B question. A proposed ocean power plant will utilize the temperature difference between surface seawater and seawater at the depth of 100 meters. Assume the surface temperature is 25 Celsius degrees and the temperature at the 100 meter depth is 3 Celsius degrees. What is the ideal Carnot efficiency of the plant? So the efficiency formula is equal to 1 minus Q cold over Q hot, or 1 minus T cold over T hot. But you have to convert your temperature into Kelvin, and 273 degrees Celsius, negative 273 degrees Celsius, is equal to 0 Kelvin. They don't say degrees, 0 Kelvin. So if you have 25 degrees Celsius, that gives you 298 Kelvin. That's for 25. And for 3 degrees Celsius, you would get 276 Kelvin. If I plug in my numbers into the efficiency formula for T cold and T hot, I have 1 minus T cold is 276, T hot is 298. So if I plug in the numbers, I get the efficiency of 0.074, or 7.4%. If the plant generates useful energy at the rate of 100 megawatts while operating with the efficiency found in Part A, at what rate is heat given off to the surrounding? We know another formula for efficiency is how much work an engine can produce depending on how much heat is given to. So work over heat in is equal to, or heat in is the hot. So if you remember, for engine there is the hot reservoir, there is the cold reservoir, and the energy is going into engine. Some is going to be for work, and the rest is going to be spilled into the cold reservoir. So this is Q hot, how much spilled from the hot reservoir. This is Q, how much goes into the cold. This is operating at temperature T hot. This one operates at the temperature T cold, and this is how much work is done. So this number is usually bigger because that's how much energy engine gets, and these two numbers together, the work and heat energy go spilled into the cold reservoir, together equal to the Q of the hot reservoir. So if you remember this part, so this work is actually this work, the work that is done by the engine, and Q in is your hot reservoir. So if you remember that part, then we're going to go back to solving the question. So now if I'm looking for heat needed from the hot reservoir, or in, is equal to work over efficiency. But I don't have work, I have useful energy at the rate of so many megawatts. So what I have is the power, and the power is how much work done per time. So if I modify my formula, how much heat given to the surrounding, and if I find this, how much heat found to the surrounding over specific time, so if I divide both sides by time, then work over time will give me power. So heat per unit of time per second is, or heat spilled from the hot reservoir is equal to the power, which is 100 megawatts over the efficiency. So how much heat is given per time is equal to 100 mega, which is 10 to the 6 watts, divided by efficiency, which is 0.074, and that will give me 1351. And again, I find joules per second, so I can write watts or joules per second, and this is how much how much heat is coming, how much heat energy is coming from the hot reservoir to the engine. The question in the problem is, let me switch the color. The question in the problem is, at what rate is the heat given to the surrounding? So what they ask you here is how much is spilled or cold reservoir. So, and if I continue looking per unit time, so I can just say how much heat per second is given away to the surrounding, then Q cold over time is equal to the Q hot over time minus the work over time, and they give you the work over time, which is your power. So that gives me, I'm just trying to squeeze it here, Q cold over time is going to be equal to 1250 megawatts. And that is over time. Then the problem continues, and it says, it's still the B part, no, the C part, right? Okay. So yeah, for the C part. So for the C part, here's where it starts. The diagram below represents the Carnot cycle for a simple, the reversible Carnot engine, in which a fixed amount of gas, originally at pressure P sub 0. So here is A, originally at the pressure of P sub 0, and the volume of V sub 0, following the path of A, B, C, D, A. In the chart below, for each part of the cycle, indicate positive or negative, with a positive or negative, or added or taken away, or 0, where the heat is transferred. So this is for the heat. So we have for the heat and the change of the temperature. And temperature change are positive, negative, and 0 respectively. Q is positive when heat is added into the system, and T is positive when the temperature of the gas increases. So from A to B, in Carnot engine, this process is isothermal. So this is isothermal. Isothermal process. Isothermal means the change of the temperature is equal to 0. So if the change of the temperature is equal to 0, and the gas is expanding, it went from V sub 0 to twice much volume, then the heat must be added into the system. Otherwise, the internal energy of the gas would change. And in our case, because it's isothermal process and temperature doesn't change, the internal energy of the gas in this case doesn't change. And because delta U is equal to heat added into the system and the work done on the gas or by the gas, in this case gas is expanded, so the work done on the environment positive. So in this case you have Q is equal to the negative work done. For BC, it's adiabatic process. So for BC, we have adiabatic. Adiabatic, so that was Q and delta T. For adiabatic process, no heat is added or taken out of the system, so this part is 0. And because it is expanding and the pressure is dropping, so the temperature is dropping or decreasing. DC is isothermal at the lower temperature than AB. So again, it's isothermal as well. So this one is isothermal. Change of the temperature doesn't change. So that means there is no temperature change. So there is no, which is 0. And for heat, because there is a compression in the volume, and in order for it to keep the gas during the compression at the same temperature, you have to take the heat out of the system, so you loosen the heat negative. And the last process from D to A, again it's adiabatic. So from D to A, it's adiabatic. That means change of the heat is equal to 0. 0, cannot write 0 right there. Let me see. It jumps to a different page. Change of the heat is equal to 0. And because change of the heat is equal to 0, Q is equal to 0. And you are increasing the pressure when the volume doesn't change that much. So that means the temperature is added into the temperature is increasing in the system.